So hi everybody. So I'm very happy to be here. So my name is yes as Philip Radim Philip said is Raffaele Silvestri, and I come from the Philip Vater Group at the University of Vienna. And I'm sorry that you won't be hearing the machine learning talk that was supposed to give by Philip, while instead you might maybe learn from this talk that that Earth rotates. But yes, at least we did it we measured it in a different way than usual. Good. So let's move on. But first of all, like how rotation is measured in general, and with respect to what? Well, uh, by experimental devices, as for example accelerometers and gyroscope, like as simple as that. And what they do measure is actually the local inertial forces acting on them with respect to the local, absolute reference frame, inertial reference frame. Good. So gyroscope are there since mid 19th century. The first prototype was built by Foucault in 1851. It was a mechanical gyroscope, and since that time, technology has advanced a lot, especially photonic technology. And now we have optical gyroscopes, so just like devices where light is probing the rotation. And nowadays, those are the most sensitive rotation sensors ever built by human being. How? Well, this is mainly thanks to the incredible power of Sagnac interferometry. So let's briefly recap what's a Sagnac interferometer. So it's a closed path interferometer where light is splitted here at the beginning. Then it splits in the clockwise and the counterclockwise propagation direction. After the propagation, if the interferometer rotates with respect to the local frame, the laboratory frame, then the two waves will accumulate a differential time delay, which will result in a phase shift of the interference fringes. So now this phase shift for any shape of the trajectory, it must be closed trajectory. It's proportional to the local rotation rate vector, and the scale factor vector, which is in turn proportional to the area vector, the effective area vector, which is a vector that has the normal direction with respect to the plane of the interferometer, and modulus the effective area of the plane, and then also like the wavelength of the light. So this effect has been extensively probed with classical light, and but it was only with the advent of the laser that Sagnac interferometry became the ultimate tool for rotation sensing. Good. So now, like to us in the quantum optics community, what the natural next step would be to ask like whether we can use like quantum states of light, right? For example, to get a quantum enhancement. This has been done only very very recently with the advancement of quantum photonic technology. So they first started by probing fiber optical gyroscopes. So just optical gyroscope, but made of optical fibers. Usually they build that to make several windings, such to increase the effective area of the interferometer, and so the scale factor, and then the sensitivity. So they probed this first with like single photon states, and then also with squeezing, like same approach as LIGO. They measured also they demonstrated also quantum enhancement, though the loop was just like 10 meters of fiber, so it was pretty small. And then after some years, just like 6 years ago, they started probing fiber optic gyroscopes, or like fiber optic Sagnac interferometers with two photon states. So they probed the Hongyu-Mandel effect, and what they actually did observe is the shift of the Hongyu-Mandel dip pattern due to the rotation that was induced by just like rotating your optical table. So they literally like built the setup, rotated the optical table at some frequency, and then they saw a shift in the home dip. Good. And then in Vienna, just like same time, this was done in Glasgow. The group of Rupert Turzin probed the same effect on a rotating turntable still, but with two photon noon states. So what I showed is the super resolution of the two photon noon state with respect to the single photon one, and and of the Sagnac phase and induced by their turntable rotating. So that's it. So now starting from here, we decided that we could try to make this better, like more sensitive, more precise. how do you make Sagnac interferometer more sensitive? You increase the scale factor, so the area. So you use longer fiber, and you wind it also on a bigger on a bigger frame. And for example, like the fiber used here was like hundreds of meters. So we thought about using like maybe kilometers of fiber. And so this is what we built. And yeah, we realized this 1.5 square meters frame, and we wounded 2 kilometers of polarization maintaining fiber around it. And so this realizes like 750 meters square of effective interferometric area for the Sagnac interferometer. And with that, you are actually able to sense the Earth rotation. And so we thought, why not like measuring the Earth rotation effect on entangled photons? Good. So this is the simple, scheme of the setup. We just generated two photons, were indistinguishable from a type 2 SPDC source, just like with orthogonal polarization, so distinguishable in the other degrees of freedom. So combine them in a PBS, then like in the same spatial mode here. So now this state was rotated by a wave plate at 22.5 into a two-photon noon state. So two-photon polarization entangled with two photons being in like horizontal and two photons in the vertical polarization, and then with another polarization being splitter, we split them into spatial modes, the clockwise and the counterclockwise propagating one. And so they were acquiring the Sagnac phase induced by the rotation of the art, which was like twice what you expect with classical light or single photons. Good. So far so good. Then they were like detected with single photon detectors, and the interference fringes were taken. So the problem here, the main issue here, is that the Earth rotation is constant, so it's always the same at least at this sensitivity level. Of course, like there are variations, but not at this sensitivity. At this sensitivity, they won't be able to see that. And so, since it's constant, you need a way to extract it just to the back from the background. And so to do that, we put like an optical switch, and we divided the whole length of 2 kilometers into equal lengths of 1 kilometer each. And here you can like flip the propagation direction here. You can have like parallel or like crossed switch, and this effectively flips the propagation direction in this spool. So which means that for equal lengths they have different propagation directions, so they nullify the Sagnac effect, so the scale factor, the effective one. So effectively what you're doing is that you have the Hertz rotation Sagnac phase, and then when you switch it you have like no Sagnac phase at all. So it's like there is no rotation. You're actually like, kind of like trick the photons thinking that they are on a inertial reference frame. So good. So then those are the fringes that we took. You see two curves. This is like just like the single photon measurement. So less interesting. So and this is like the two photon measurements. You see the super resolution that you actually do. That you actually like do expect, and then like here you have to zoom in to see that there are two curves, one for the switch on, one for the switch off. So signal on, Earth rotation on, signal off, Earth rotation off, and then you see a fringe shift if you fit the points. And this is like exactly the rotationally induced like Earth rotation Sagnac phase that we measured. If you compare it to the single photon ones, it's then like twice. So important is this is done for one angle. So as I showed you, we had this frame. We could rotate this frame, and it's important because you have to rule out the systematic effects that you have just at one angular, and to actually also probe this dot product between the fixed Earth rotation rate vector and the area of your interferometer, so the cosine behavior. So we took like several points at different angles from minus 90 degrees to plus 25 degrees, and we did it with single photons and with two photons. Then we fitted the two curves, and we had the two separate like single photon and two photon measurements, which of course like is two photon measurement being like twice as big with respect to the single photon one. Good. Then what actually is 5 milliradians? How does this like transfer to rotation rate? Well, that's what we measure. So the length of the day is actually like around 24 hours, as we know, and the uncertainty is like 1 hour and a half. So yeah, basically, yeah, it could be 26, 20, 22. It's still like a very, very, not accurate, not precise measurement. but it was still the first time that was done with entangled states. So there is still a long way. There is still a really long way. So this is like just like first stepping stone for like much hopefully much better measurements. And this was published just almost a year ago now. Good. So this plot just like compares the sensitivities, so the rotation rate resolutions achieved by Sagnac interferometers using quantum states of light. This is the Earth rotation threshold. So the previous one were here, and we are here. So just like one order of magnitude below. Then also 3 months later, another experiment came up where they measured the Hertz, where they measure the rotation sensitivity to the zeptosecond scale. If you transfer to time delay, this is actually comparable to our sensitivity, but with just like with a smaller interferometer and with single photon states. Good. And after there's nothing done with quantum states of light, so we're so far the best now. But you have classical fiber optical gyroscope, which are much better than ours, and they fill this gap here. And but the idea is trying to reach this threshold, which is called the GR threshold, which is the sensitivity region where you expect some gravitational effects coming up. So gravitational effects, namely like geodetic or frame dragging. So her space-time that rotate that it's dragged by Earth, and this gives a correction to the Sagnac phase that you will be able to measure if you would have sensitivities 9 orders of magnitude better than what we achieved. And actually, I'm working on a proposal on the feasibility of building such a Sagnac interferometer, which would have to be giant, like huge, and so this is like challenging. Yeah, good. Yeah, I can end. It's like 12 minutes. Yes, it's fine. Yeah, just wanted to say that they're also doing this gravitational experiment with a Mach Zehnder, trying to measure the gravitational potential difference with the known states now, and it's going on in the labs. That's it.
Thank you very much. Questions?
I'm wondering why not using two-mode squeezed light, lots of photons. You can start with the classical experiment, then add 3 dB of two-mode squeezing and get twice as good as they.
Hmm.
But for some reason, you limit yourself
No,
to
yeah,
single
it's
photon.
I completely agree, and it's something I'm very interested in investigating and doing. So I completely agree. This is a great what you say. It's a
So,
great approach. Like it's
yeah,
just because of the expertise of the group, which is on like single photon generations, and still like it was natural to start
but
with that.
then you will have to be measuring for a relatively long time,
Yeah,
as
we
I
so
understand.
this measurement was 2 weeks. So it's still like we had to count photons for like a long time. And for example, like for the GR possible like GR measurement that would need, of course, like a very big gyroscope, you would need like more than like 2 months of stable interferometer. So in seeing the single photon like regime, we're always limited by count rates, and they're very low. It's just an approach, but it's not the superior to others.
All right, one quick question, David.
In the last plot that you show the various results, including also the classical one, are there also, for example, laser gyroscope? So how you compare? No, this is a passive gyroscope. No, when you inject light. Instead, when you have situation, so it's possible to improve having some sort of quantum laser gyroscope that you generate inside. No, because many geophysical applications they use laser gyroscope rather than passive
Yes,
gyroscope.
yes, yes.
So how do they compare for reaching the general relativity?
Okay, yeah. So exactly as you said, these laser gyroscopes are the best rotation sensors ever built, and they are already here. So there was like a recent paper by the the Ginger collaboration. So they built like a ring laser gyroscope in the Gran Sasso in center of Italy, and they claim they had like 2 orders of magnitude sensitivity below that threshold. Of course, this is like a laser. It's like there's, I mean, like still nothing quantum, and the natural thought is like, what about like maybe probing these cavities with photons. The problem is that photons are quite broad, so you would need like very very narrow photons. You will lose lots of them, so it's like also very challenging
I
to do
think
that.
that will be for maybe longer discussion. Thank you for your answers.